next speakers are Leslie Robertson from Leslie Robertson Associates and David Malott from Con Pedersen Fox. It's my pleasure to have them both on stage today. Les has been with the Council for more years than he probably wants to tell us. In fact, Les was a past chairman of the Council. So I'm not sure who's starting first. Oh, David's starting first from Con Pedersen Fox. So could you please put your hands together for Dave Malott from KPF.
Okay, thank you very much. Yesterday we heard a great presentation on a truly pioneering building, Burj Dubai, and I must compliment the entire team on the level of thought that went into the building. But let me transport you for a moment to Shanghai, where we are building what will be the world's tallest building, but only for a short time, in as much as it takes the Burj Dubai to be completed. Now, Shanghai, like Dubai, did not really exist in its present form when we started the project. This is a photo from about 15 years ago. The only landmark that existed was the Pearl TV Tower, the one with the stacked spheres. SOM was planning their Jin Mao Tower, which is outlined in red. That was our context. So we chose to somehow develop a relationship between our project and the Pearl TV Tower to create a dialogue between these two structures so that the building did not stand alone by itself, but rather spoke across this urban space, and then the dialogue between these two buildings would then unify the skyline. So we carved a big window at the top of the building that then faced the TV tower, and the idea behind this window would be that it relieved the tremendous wind loads at the top of the building and therefore greatly making this height structurally achievable. And then that this window would then be a connection to the cosmos, almost like a sundial. We called it the moon gate, so something that also not connects to the city, but to something beyond. Now, this project gained a lot of press because it's being built by a Japanese developer in Shanghai, and the circle was seen as something else other than the cosmic connection or this wind gate that we intended. So the question was what to do with this circle. Now, this, of course, is a joke, but we did consider at one point to put turbines in this void to try to capture the wind. But when we actually looked at it, and this was discussed yesterday in some detail, is when you think about the embodied energy that goes into, first taking the material out of the earth, refining it, transporting it, and the workers, all the people involved in that process, and then the food that they eat, when you add all that together, is the output of that turbine really equal to what goes into it? So I call this the sustainability of addition. I think a lot of trends now are to add double walls, is to add photovoltaics, is to add a lot of stuff into a box. But what I'd like to talk about today is sustainability of subtraction, in which you take out everything from the building which you don't need, and then trying to find in the form and the function and the engineering of the design an inherent sustainability. And then maybe there is some truth to this old statement. So essentially, this project is an abstract sculpture. It's a monolith brought to life and clad in glass. It's the Woolworth building, this sort of classical tapering tower, stripped of any ornamentation. The form itself is very simple. It's a square shaft that's been carved away, so, again, subtracting those parts of the building which you don't need. The geometries themselves are very rational, and then the form is one of purity. By shaving away the building, by carving it, it yields a range of floor plates then which are then suited for the office in blue, transitioning to a hotel where you actually would prefer this bar shape in red, and then finally to the observation areas where you really just want a long shape which then maximizes the views. So really the result, I think, is one of a sort of timeless purity that really recalls some of the primal beginnings of architecture in tall buildings. Now, as David Scott mentioned, this conference has been a great place in terms of talking to people, getting new ideas, and using that to refine your own thinking. Lee Morris had a very great presentation talking about the dire state of the climate if we continue our current approach. So I was thinking about how do we do things not one building at a time, but across the board in one big sweep. How do we make sustainability scalable and as well as affordable so that clients will be interested in this? So the idea to, again, subtract rather than to add. So if you think of the construction cycle, Burj Dubai was 3 days, Shanghai Financial Center 4 days, only made possible if the forms are rational and systematic. And if you do feel compelled to twist or lean your tower, to do it in a very intelligent way. I know David Scott has found some great ways to do this, and I do hope you get to make your presentation someday, David. From Joe Curry at ALT, who was a great contributor to our project, Nusa Burj Dubai, he proposed, let's look at the safety factor. Safety factor it's dictated by code. It's applied to your project. So the engineers now with computers and testing can know exactly how much structure you need. But there are these building codes in many places of the world which predate the computer and then require to take what you need and multiply it by 2. And then isn't it time we revisited those codes, and what kind of money would that save us? Less energy. I talked to the Sustainable MEP group on Monday and proposed, what if we were to change the thermal band? Can we, as inhabitants of a building, accept a building to be a few degrees hotter in the summer and a few degrees colder in the winter? What kind of savings would that be? The consensus was that would be exponential. And less luxury. I learned this from staying in this hotel. While it's a great hotel, do we really need the entire foyer to be clad in marble? And finally, less engineering. And I think this is really, you find a good engineer. And what I mean by less engineering is an engineering that is extremely elegant. I think the best engineers I work with are those who have found the simplest solution. And it's often the simplest solution that's the hardest to find. So this leads me into introducing Les Robertson, who was our collaborator on this project. This is the Swiss watch that William Baker referred to yesterday. So this is looking behind the facade of the watch and seeing the gears on the inside, what really makes this building tick. Now, the original design for this structure, the tower was originally 460 meters tall, was essentially a concrete shell with punch windows, extremely heavy, and it didn't quite fit into the image of the building as one of transparency and glassiness and simplicity. So when the building had to get even taller, and the foundations at this point had already been put into the ground, is when we engaged Les Robertson, a great structural engineer, I also think a structural magician, because he took this structure and he made it disappear. Okay, Les?
Well, I guess the role of the structural engineer in improving the energy consumption is mostly the reduction of materials that go into the project. And I was going to tell you that we're motivated by such thoughts that we had worked very hard to reduce the material in the project. But David let the cat out of the bag when he pointed out that the foundations had already been installed and that we were going to build a bigger building on the existing foundations. The project had a kind of a tumultuous history in that it started with concept designs for the structure done in New York and all of the architecture work done in New York. And then structure, MEP, and so forth all moved to Japan. Designs were completed. As Mr. Malott pointed out, the foundations were installed. This was the piling. At that time, a major Japanese company, Nippon Steel Company, came to us asking if there was a better way to do the structure. And we thought about it a little bit. We said yes, there was, and produced some designs. And just at that point in time came the Asian financial crisis, and the project went on hold. And when it came back to life again, the developer, Mr. Mori, had decided he wanted a bigger building, which is fine, but the problem was that the foundations, the piling, had been installed, and the government in Shanghai was very reluctant to allow further piling to go in place or to allow enhancement of that piling. A part of that because right across the street is a major hotel and the wonderful building designed by Skid Moorings and Merrill, the Jin Mao building. So noise was an important factor. But making the project bigger meant that we had to make it lighter. So the figures don't look overwhelming. That is, 16% in the floor area is not a huge amount. But when you add that to that, the added height and the added overturning moments from the wind, the existing foundations were a significant obstacle to the design. And so we started out by saying, well, what can we do to reduce the wind loads, not by making less windy, but just by making more rational the building code. The regulations in Shanghai were quite conservative, basically organized about 30-story buildings. And so we went at it with a deep research project. We met with the wind engineers from all over China and were able to get what we thought was a significant reduction, that is from 1, if you will, to 83% of that. And in fact, our prediction was substantially less than that by about 43%. A lot of wind engineering work was done. In fact, that was essential, absolutely essential to the design. Those of you who work in high-rise buildings know that wherever you are on the planet, wind engineering is the ultimate decider of the structural system. Now, the original design was kind of like a perimeter of structural steel, a la the John Hancock building in Chicago, the core of reinforced concrete. So in order to really reduce the weight of the building, we realized immediately that we had to increase the stiffness of the outside wall quite significantly so as to reduce the requirements on the services core so that we could take a lot of concrete out of the services core. And David showed you this model. Not shown here are all the less significant floors in the building. This model was actually produced in order to better explain to the seismic experts of the People's Republic of China something of the technique for resisting the loads from earthquake. Notice that we had installed 3 levels of outriggers in the project, which produced a significant reduction in weight. Existing piling was laid out assuming that there would be loads from the services core and then 4-point loads at the corners. And we realized that we had to enhance not just the piling, but we had to think about how that load was distributed to the piling. So we put in a distribution network above the mat foundation so that we could take loads from the services core and distribute them outward, and conversely loads from the exterior wall and distribute them inward. This is one of a variety of distributions that we tried looking at how we would divide the load between the services core and the perimeter structure. Now, Well, fundamental in our belief for the design of a major building is that it be very robust and that it be very redundant. And so our approach to this was to use small columns on the perimeter of the building and to transfer those, the loads from those small columns to major columns, mega columns if you will, in the corners. In this way, we could design the building so that we could take out all the columns, the little columns, at any level of the building, and it did not result in further collapse of the building itself. And conversely, we could take out these distribution trusses. We could remove one, and still the structure would remain stable. So the kind of robustness and redundancy was fundamental to the design of the project. And here you see up in the airways one of those belt trusses going in place on the left side of the screen. We used outrigger trusses, and normally outrigger trusses are organized so that they cross the services core, and there's nothing wrong, perfectly good way to do it. But in this case, for a variety of reasons, largely because of the shape of the building, the services core was laid out across the diagonal, and therefore was not practical actually to carry the outrigger trusses across the core. So we carried them around, and the truss work that you see here in red is in fact ultimately buried in reinforced concrete. And in the services core, we had a similar thought, and that is, again, the columns that support the loads in the center of the services core are transferred every 12 or 15 floors out to the walls of the services core itself. And again, designed so that if something should happen to one or more of those columns, it did not result in a catastrophic event in the building. In fact, if one of the trusses were taken out, again, it did not result in a catastrophic event for the building itself. And there was a further advantage, and that is now all of the basic load carrying capacity in the building is in reinforced concrete. And by using appropriately equivalent concrete strengths and properties in the core and in the mega columns, then the issue of differential shortening between the various columns is reduced quite significantly. And also, all of the steel columns can be made quite small because conceptually they're the same height from the bottom of the building to the top and designed to carry their immediate load down to a transfer truss, and also, of course, to be able to step to the front and carry additional load where required in the event of the failure of other columns or trusses. The services core steps back in order to, as the building steps back and in the same direction. Now, those of you who work in earthquake design realize that lateral transfer of shear walls is a significant problem, and that was done through a variety of techniques worked out in considerable detail with the seismic experts of the People's Republic of China. These big columns in the corners of the building are in fact big columns. They are, because in fact they are carrying, in essence, almost all the weight of the building in reinforced concrete. So these columns have a dual function. They tie together the structure, the structural steel, a brace structure, which is on the perimeter, without the need to create three-dimensional connections in the structural steel. So if you look at the columns here, you see they are separated. They are not, in fact, connected except by bonding them together through the reinforced concrete. It's a kind of a moment-free transfer between various elements of the structure and bonds the entire perimeter structure into a single structural element, but without the need for those three-dimensional connections in structural steel. And here you see in the full scale one of those columns. The construction was, as Mr. Malott said, roughly a 4-day cycle for the building, and major structural steel components. The connections of these major elements was accomplished in a way that is in some ways unusual, and that is these are all box members, but the members in the horizontal plane, well, the members that are in and out of the picture, are in fact not connected at the ends. They're used to stabilize the box section, and of course they contribute to the L/R of the members, but they are not in fact connected. And this is done simply to save money, to save material. As the requirement for the box section is, in terms of strength, is on the 2 side plates, not on the remaining 2 plates. Seismic design was a very major consideration in the project, although Shanghai is not a great seismic center, but the Chinese experts and ourselves both were concerned because the building was substantially outside of the experience of the People's Republic of China. And so many different kinds of earthquake analyses were performed. This is an example of just one time history analysis. We did many. This is a comparison of the shear in the building for, I think in this case, 4 of the various time histories that were accomplished. And the response vector is kind of interesting. We were quite surprised because when we put a bunch of them together, we found that the Chinese code and the kind of average of all these was more or less in line. Now, our structure is way out in the end here. We're in the 6.5 second period range. So the differences were not significant, but I know some of you who attended the session yesterday afternoon appreciate the fact that these are great uncertainties. The actual waveforms that the structure need respect are quite significant. We modeled pretty much everything in the building in order to understand fully the behavior of the project. And one of the more interesting ones is the pushover test. Those of you who are not into such things, you imagine the Jolly Green Giant starts leaning against your building and he pushes and pushes and pushes until it falls over. And so this is actually an early rendering of the pushover curve. For the rare earthquake, we had a certain level of deformation, and then we started to develop moment hinges in some of the walls, and then the mega diagonals. None of these are really critical to the stability of the building itself. And then more wall hinges, and then ultimately we started getting mega column hinges, and then you start worrying because you realize those are going to lead to ultimately to the collapse of the building. But you see, that's almost 4 times the lateral deformation expected in a rare earthquake. David didn't talk to you about the shape of the hole at the top of the building, and if you want to know about it, you'll have to ask him because I refuse to answer that question. But the original, what did we accomplish? Well, the original building, if we stood on the inside and looked out, it was, as I said, a kind of a Sears Tower structure, very satisfactory structure. Nothing wrong with it at all. And we changed it to be like this. We used 3 small columns instead of multiple large columns. And then, of course, there's the diagonal that crosses all of the faces except the curving face that ultimately ends up the broad face of the building. Structural steel weight, I show 3 here, one as originally designed, and then using the brace system, and then the brace system with outrigger trusses. So you see we obtained at least a modest reduction in the weight of structural steel in the building. More important was the total building weight, which we were able to reduce while still making the larger building. And then some construction photographs. And then I wanted to thank everybody for coming today, and mostly we need to thank Bill Pedersen, who was the conceiver of this architectural forum, and David Malott, who was instrumental in making it happen, and Paul Katz. And from our perspective, all of the wonderful people in our company, but most importantly, Sawteency, our partner in charge. So thank you very much.